Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome, everyone. It's my great pleasure to introduce Dean Towson. Dean is a professor at UCSD. He's done great work in simultaneous multithreading and other multithreading that has impacted the computer industry a lot, and he is here to talk about event-driven simultaneous compilation today.
All right, thanks, Honor, and thanks for the opportunity to come talk about some of the things that we've been working on. So today I'm going to talk about event-driven compilation. But before I actually tell you what that is, I'm going to motivate it. But I'm going to motivate it with a pretty wide brush, because I'm actually going to talk about things, well, that you probably already know, but also things that motivate a lot of the research that we're doing. And so the point is that, for a large number of years, we've been taking sort of Moore's law, all these transistors, and applying them almost exclusively to getting more and more single-thread performance. But that has pretty much petered out, and the microprocessor industry has taken a pretty sharp right turn, and to the point where actually we're no longer applying Moore's law at all to single CPU performance. And in fact, applying all those transistors now, maybe even taking some transistors away, and applying those to increasing the number of on-chip contexts. Certainly multi-core, but also multi-threading, likely combined with multi-core. And so the point is that if we want to stay on the, on the performance curve, which is the corollary to Moore's law, that it now becomes completely dependent on our ability to create thread-level parallelism. And it's important to stay on this performance Moore's law for a number of reasons, and I think particularly important to a company like Microsoft. Obviously, once we start sort of riding this performance curve, Intel and AMD start selling less chips, and every time they don't sell a chip, there's Microsoft software that is not bundled with those chips. So I think it's important for a number of reasons to sort of to do everything we can to stay on this performance curve, but in order to do that, we've got to have parallelism. So this leads to what I would call a parallelism crisis. And what I mean by the parallelism crisis is this gap between the parallelism that's available in the hardware and the parallelism that actually exists in the software in certain environments. Obviously, there are environments where there's going to be no parallelism crisis, right? If you're Google, you're not so concerned about this crisis. And certainly a lot of server workloads, but on the desktop and a lot of other environments, there definitely is going to be a crisis. It's also worth noticing that this is not the first parallelism crisis. We certainly experienced a crisis that completely fits this definition, which was an ILP parallelism crisis a few years ago, where we started building 4-issue out-of-order processors, but running software where we're lucky to get one instruction per cycle out of that. And there were several things we did to try and address that crisis, certainly multi-threading being one of them, which now actually goes to some extent to make the new parallelism crisis a little bit worse. But this gap is actually not that big, because we got to the point where we built 4-issue processors. It turned out to be very, very difficult to build anything wider than a 4-issue processor, so there's a limit to how big that gap could be. But now, as we get to the thread-level parallelism crisis, this gap, there's really no limit to how big this gap can be, because I don't see any real practical limits to building chips with very, very large numbers of processors on them. And so now this gap, suddenly the thread-level parallelism crisis, I don't see the same limits in terms of how big that gap can be. And so it needs to be addressed. And certainly it's being addressed in lots of ways. And certainly there are traditional ways of attacking it with better and better parallelizing compilers, better tools, better languages, et cetera. But there are also non-traditional ways of creating parallelism. And my italics here are intended to indicate that I'm a lot more interested in the non-traditional parallelism. Although I know there's great work going on here, and I support that work, but our emphasis is more on non-traditional methods. So let me define what I mean by non-traditional parallelism. So first defining parallelism. Parallelism just meaning that I have something to run, and if you give me 8 contexts, hopefully I can run it faster than if you just give me 1 context. And that's my definition of parallelism. So traditional parallelism then would be I take those contexts and use those to offload computation, right? So now I've spread my computation across 8 processors instead of 1, and hopefully it runs a little bit faster. A non-traditional parallelism, right, at least one definition of non-traditional parallelism, is I use these extra contexts or extra threads to speed up the computation without actually changing the original computation at all, or at least without offloading of the original computation. And this has some really nice advantages over traditional parallelism. One of those is that nearly any code, no matter how inherently serial it is, can benefit from this parallelism. It also provides a really powerful and dynamic parallelism, which is what I wanted to say there, in the sense that, and I think we're going to see this more and more when we start putting, large parallel machines on a desktop, et cetera, is that the number of contexts available to run our job is going to be very dynamic, right? And with real standard parallelization, it's hard to deal with the fact that I have sort of 8 threads available now and 4 later and then 12 after that. But non-traditional parallelism, we can sort of take these threads away and add threads all the time, and we just dynamically use whatever's available. So let me give you a more graphical example. So this is a thread, in case you couldn't tell what it was. And traditional parallelism says, I'm going to take that and just sort of spread it over 4 CPUs. And hopefully these things can execute in parallel and I get a speed up. Non-traditional parallelism says that the original thread doesn't change, or at least it does all the original computation. And I have these things that have been called helper threads that accelerate the execution of this guy. And so I run things in multiple contexts. This thing gets faster, but this is still the original computation. So it's still parallelism by my definition, which is lots of contexts, things run faster. But it has some nice properties. Okay, and here's some examples. We've done a lot of work in this area before, something we called speculative precomputation, and doing it in hardware dynamic speculative precomputation, but a lot of other people have worked in this area as well. And traditionally, the type of things they have done is pre-compute load addresses and prefetch, or even do some branch pre-calculation. Okay, so now event-driven optimization or event-driven compilation, what I'm talking about today, is a similar concept in the sense that we're going to use helper threads to make the original thread go faster. But the way we're going to do this is to use these threads to now recompile or change the code that the main thread is running, right? So not to offload computation, but just to optimize the code so it runs faster. And this optimization, reason it's called event-driven, is going to be triggered by interesting things that go on in the hardware that the hardware can detect. So you're running along, the hardware notices something interesting about the way the program is running by the particular runtime behavior. It forks a thread. That thread goes, changes the code, and then goes away. Okay. And so graphically, what's going on is we have this original thread. We notice something interesting. This compilation or optimization thread runs. It changes the original code, right? So that when we run this code again, hopefully it's running a little bit faster. We continue to spawn interesting threads when more interesting things happen, and hopefully the original code now gets faster and faster. So again, it's accelerated because the code is improving and adapting to dynamic behavior, as opposed to, again, offloading computation. Okay, and so the really interesting thing here is that this is also a very new model of compilation in that execution and compilation are taking place in parallel. Okay, all right. So that's my definition of event-driven compilation. I have to do this. I always hate to shortchange other things that we're working on, and I want to at least tell you some other things we're working on. So if I talk to you later, you might find these other things more interesting than the thing I'm talking about today, and we can talk about those things. But it won't take long. I've just chosen some things I can do in one slide or a quick animation. But we do have this theme for a lot of the work we're doing, which we've called holistic design of multi-core architectures. And I know it's a very California-sounding word, but I'm going to tell you why that's actually a good description of the things we're doing. Things that fall under that are heterogeneous multi-core architectures, which some of you might have seen. I know Rakesh Kumar, my student, has come and talked about that. Conjoined core architectures and some scheduling we did for CMPs of SMTs. So let me tell you what I mean by holistic design. In the the not so long ago world of that was dominated by uniprocessors, we had a lot of constraints that we placed on that uniprocessor. We expected this thing to have, certainly very high general purpose performance, be able to run a lot of things really well. I also expected it to be energy efficient, reliable, and available, all these things. Okay, but now, we're putting a bunch of CPUs and putting them on a single processor, and yet if you look at the initial designs, they tend to be still applying all of these constraints to a single CPU. But the reality is that that's not really necessary anymore. We really only need to apply these constraints at the processor level. Because the customer, for the most part, as long as this thing is giving a really good general purpose performance, as long as it's reliable and available and all these things, he doesn't care what this particular CPU is doing. And so now we can design these cores and the entire processor differently if we do not apply these constraints to individual pieces, whether it's the CPUs or parts of the memory subsystem or even parts of the interconnect. And all we really care about is that this thing as a whole provides these characteristics. And so now this gives us great freedom to actually design, to architect CPUs, the interconnect, et cetera, differently, because now we are doing this, what I'm going to call holistic design, where I'm designing this particular core to be an effective element in an entire processor that gives me high general purpose performance. But I don't really care whether this core actually gives me high general purpose performance by itself. Okay. So one of the elements of this is what we call heterogeneous architectures, or at least an example. A homogeneous architecture, despite the characteristics of the applications we have to run, some with a lot of execution resources demand, some with a few, they're all going to run on the same processor, and some use it really well, and some are going to use it really poorly. On the other hand, a heterogeneous architecture is one that has cores with different execution characteristics on them, also different efficiencies, different amount of area, different energy demands, and we can take different jobs with different execution resources and apply them and run them on the cores that match those characteristics and get much more efficient execution, better performance with the same area or the same power, et cetera. That's heterogeneous architectures. And so we've looked at it sort of in the context of power, where we can actually see orders of magnitude increases in performance, energy performance efficiency when we have particular applications that have low resources demands, which there's plenty of out there. And certainly the types of things you can never do with clock gating or even voltage and frequency scaling. And from a performance standpoint, we find with a given area or a given power constraint, we can get significantly better performance. And something that I think is really important going forward is one of the things that we're going to have a hard time doing, especially with homogeneous multi-core architectures, is providing an architecture that gives you good performance, whether you have 1 thread or 10 threads or 100 threads, because you're really going to have to pick a design point in terms of thread level parallelism and optimize for that. Whereas with a heterogeneous architecture, you can have an architecture that's going to give you good single thread performance, but also has lots of little cores, so you get real high peak performance as well. Okay. And in terms of scheduling, one of the interesting questions we asked is, well, let's suppose you had a homogeneous architecture that was all multi-threaded cores. Could you get some of the benefits of a heterogeneous architecture? And the way you do that is by scheduling things in such a way that threads with low resource demands get mapped, to a place where they get essentially a small virtual processor, right, where they're sharing the resources, and things with high execution demands get mapped to a processor where they're not sharing the resources with other threads. And the interesting thing about this is that this makes a lot of sense when you think about this, particularly in the context of heterogeneous architectures. But any reasonable operating system scheduler at this point is not going to consider this a reasonable schedule, right? It's going to say, first thing I need is to load balance and make sure, if I got 5 things to run and 3, I'm going to do 2, 2, 1 or something like that. But it's always going to really seek to have balanced schedules. And what we've shown is that almost invariably, if you have a real diverse workload mix, the best schedules are actually unbalanced as opposed to balanced. And so you need some kind of scheduling mechanism that's actually going to consider unbalanced schedules if you want to find the best one. Okay. Conjoined cores. Okay. The last element of my holistic design is one of the assumptions that certainly has gone into existing cores is that not only are all the cores the same, but they're also separable, which means that I can say this is core 1, this is core 2. But really, once you put them all on the same chip, you don't even need to do that. And we found that the modern processors, because they tend to be highly over-provisioned, right? They're not designed for the average application, but you design the floating point unit for a floating point intensive application, the instruction queue for something with a lot of parallelism. You design the number of ALUs for something with high throughput. You design the memory subsystems such that things with large working sets run well. And so every element tends to be somewhat over-provisioned. And what we find is that if we do sort of naive multiprocessing, we now tend to multiply that over-provisioning times the number of cores. And so now everything's over-provisioned. Instead, what we can do is take some of those over-provisioned resources and share them between cores in such a way that we have the same level of over-provisioning available to a single core. Right? So if this particular core happens to be running something that really needs high floating point throughput, it's still got it. But we amortize it because it's actually shared between adjacent cores. And even if we do this really conservatively, so that we're only sharing really big over-provisioned structures, although it's a little surprising what we considered over-provisioned. Because like the floating point unit was really obvious, but we actually also share the L1 instruction cache and data cache and the port to the L2 cache interconnect. And we actually find we can double the number of cores on the die at a pretty small cost in performance per core. Okay, so sorry for the digression, but I hate to shortchange anything we're looking on to just in the interest of creating a coherent talk. So, but let me get back to event-driven compilation. And the thing I wanted to say at this point is that this work was done in collaboration with Weifeng Zhang, who was a student at the time and obviously did most of the work, and who is now here, as well as Brad Calder, who is also now here. But I understand Brad is watching this remotely, so he cannot argue with anything I say. But I guess Weifeng can. Okay, so as I've sort of talked about, event-driven compilation is now a real new model of compilation, a new model of optimization, where the computation and the compilation go on in parallel. And it's event-driven in the sense that optimizations are now triggered by the hardware identifying interesting runtime behavior. And so there are a lot of advantages, and these advantages are really intended to be relative to some dynamic optimization systems that, at least up to this point, don't actually run in parallel and are not event-driven. And so what the advantages are, first of all, that we get real low overhead profiling of runtime behavior because it's happening in hardware. We get low overhead optimization because it's running in another thread and doesn't stall the main thread. We get real quick responses to the program's changing behavior. And all these things allow us to do really aggressive optimizations that you would never consider doing with existing dynamic optimization systems. And so the effect you get in current dynamic optimization systems, if you're familiar with Dynamo, things like that, is they tend to start out running really slow because they're doing a lot of monitoring. Dynamo, for instance, starts out by interpreting the code, so it's running really slow. Eventually, it identifies control flow paths that are real common, and it creates these hot traces that it puts in the code cache. So it goes from monitoring, executing really slowly, to now compiling the code, in which case the main thread's not running at all. It eventually gets to the point where the main thread is running at a pretty good clip. But there's a real heavy expense to doing these things, not just doing these different things that are not execution, but also context switching between these different phases of execution. And so one of the implications, there are a couple of important implications of that. One is that you're going to stop monitoring as soon as you possibly can, because monitoring is so expensive. They're even doing it through interpretation. But even if you're not, if you're doing it in software, it's going to be really expensive. And so as soon as you sort of decided what you think the interesting behavior is, you're going to stop doing it, and you stop monitoring. And the other thing is that you're going to do really unaggressive optimizations because you don't know if they're going to pay off, because the program has actually stopped while you're doing that. Because we never stop the main thread. The main thread is running full speed from the first microsecond or before. We can now do real aggressive optimizations. In fact, the most aggressive optimizations we do have virtually no slowdown for the main thread. Okay. All right, so the execution model is this. We start out actually with highly optimized original code, and the main thread is running that code. We've got hardware that's sort of watching what's going on. Something interesting happens, and we spawn this helper thread that now goes and, assuming that this runtime behavior that we've identified continues, now optimizes the code to take advantage of that runtime behavior. So now we have some more optimized code. We continue to see events. We continue to change the code, and we're doing this. If you're familiar with dynamic optimization systems, we are doing this in the context of hot traces and in a code cache, so that we're creating traces and then we're optimizing those traces, and it actually makes the compilation steps being done by the helper thread real straightforward. Okay, and so then the code gets better and better over time. Okay. All right, so that's the introduction to what we're doing. I'm going to talk about 4 optimizations. This one pretty basic, and then these are sort of new optimizations that we've done in sequence. By the way, please stop me if you have questions. So again, the framework, I think actually most of this we've talked about. Yes.
When a thread, when the optimizer kicks in.
Yeah.
So that thread stops.
No, so we're assuming a multi-threaded hardware. Being multi-threaded meaning simultaneous multi-threading or multi-core.
But the first thread could continue on executing a particular method, which is then being optimized by the optimizer.
Right, but it's being optimized in the code cache, right? So it's being optimized in a separate place, and so the original code is still there. In fact, the original code is always there in case you need to fall back for some reason. And then so the very last thing that's done is that the first instruction of the original code is changed to a jump to the new code, right? And so until that jump happens, you can play with the code all you want, right? So there's this specific instance where the changeover happens, and there's no intermediate period where things are out of sync. Okay, but good question. Okay. All right, and the same thing happens when we re-optimize the code. We'll leave the old hot trace, put in a new hot trace, and again change the original pointer at the last second. Okay. Okay, so this is what the architecture looks like. And there are several pieces. I don't think the hardware is overly intrusive, given that we are moving towards the point where we're adding more and more monitoring to the hardware anyway. And so the first thing that you're going to do when something runs that you want to apply Trident to, which is the name of the whole framework, is that you want to sort of register this thread as being one that you're going to apply these helper threads to, and you're going to create helper thread context, which basically means you're probably going to set aside some stack space and things like that for them. And so you're not actually allocating context or anything to them, but you want to have the ability to start up a helper thread fast when you actually see an event. Okay. Then you start sort of monitoring to see what's going on. You have some hardware which is going to identify events. We'll talk about what those events are. Put those events into the queue, although we actually found that we don't even need an event queue, because if we just sort of ignore events that come while we're doing optimizations, even if there's no, and there's no helper thread to actually take those, that they pop up again. If it's an important event, it just keeps popping up, and so we gain almost nothing by actually queuing up these events and coming right back to handle to empty the queue. So don't even need that. But eventually now, you get an event, you spawn a helper thread to take code out of the main thread, put it in the code cache, and optimize it. Okay. All right. So what are the events? And again, there's all kinds of things we can actually do, and I think this is a really powerful framework. But specific things that events that we handle. The first thing we handle are hot branch events, and so this is how we actually create the initial hot traces in the first place. We identify popular control flow paths in the code and create a hot trace based on that. But we also have this additional event that does give us another advantage over other dynamic optimization systems is that it's easy to sort of monitor these hot traces and actually see when we're frequently sort of dumping out of those traces earlier than we'd like to, which implies that the trace is no longer following a real likely control flow path. And then specific optimization events that we deal with are hot value events. We'll talk about what those are, as well as delinquent load events. And this tells us that, in the case of the results we have here, that loads are frequently loading the same value. And this tells us that a load is frequently missing in the cache. And so it just turns out that so far we're particularly mining expensive loads, which of course is a very rich area to be mining. Okay, so first I'm going to talk about hot trace formation, which is the thing we do when we get this hot branch event. And then this becomes the basis for everything else we do, and allows us to now do our optimizations on hot traces instead of generic code. Okay, and so it's built on a somewhat traditional dynamic optimization system, which means that we're going to generate these hot traces, which are sequences of basic blocks that are typically executed consecutively, and they're stuck in a code cache. And yet, even with these basic optimizations, the Trident has key advantages over previous systems like Dynamo. So one of those is that we have hardware monitoring to identify these hot branches and thus these hot traces. The monitoring is basically free from a performance standpoint. The optimization itself is almost free as well. And there's no context switching between these different functions, because this is happening in hardware, this is happening in another thread. Okay. So what is a hot trace? Probably don't need to describe this, right? But it's just a series of basic blocks that are typically executed consecutively. And so we then have, once we create this hot trace, we then get this very sequential sequence of code, right? Typically with, sometimes we allow loops, particularly in some of the later optimizations. But for the most part, this is like a hyperblock with one entry and multiple exits, which means that the analysis on this code is extremely fast, because you don't have cycles, you don't have iterative compiler analysis, usually just one pass. Okay. So now we've got some hardware to monitor these hot traces, and I'm not going to tell you exactly what that hardware is, because I'm more interested in the concepts at this point. We could certainly talk about that if you're interested. But the idea is that we capture these hot branches, which means it's a branch where the target is a good candidate to start the trace. So it's a branch that's frequently taken, for example, and now the taken target is a place that we want to start just because we know this code is now frequently executed. Because the other thing we capture is, once we've decided this is a hot branch or a good starting target, is we capture these bitmaps that describe the control flow following this hot branch. And now this is actually another advantage over existing dynamic optimization systems, in the sense it allows us to make sure that we're actually creating a hot trace that has a frequent path. And so most dynamic systems at this point, dynamic optimization systems at this point, will identify a hot branch and then just sort of capture the very next control flow that is taken, even if it's an unusual control flow. Whereas we have the ability to now do some voting and decide that this really is a frequent path. It turns out we don't need a whole lot of instances to get a consensus, but at least we do capture a consensus, and so we tend to create higher quality hot paths, hot traces. Okay, so there are a number of optimizations that we do on these hot traces that are well documented in the literature that most of these dynamic optimization systems do. And there's some other things that are new and really aren't that specific to our system, but yet there were optimizations that new optimizations that Weifeng did that actually increased performance significantly. Dynamic optimization systems that do some optimizations to get away to eliminate, for instance, unnecessary call and returns. So you have a hot trace that has both a call and return in it. You can actually make those go away and shorten the code. But then if you sort of exit in the middle of that out of the hot trace, then the return address stack gets really confused, and your mispredict rate goes through the roof. And so we did some things to still get the effect of removing the call and return, but yet have the return address stack stay consistent. And just being real careful about where you put these traces in the code cache, using a little bit of hardware support gave us much better performance. And the ability to invalidate a trace that's not doing the right thing anymore. Okay. All right, so that's a basic hot trace formation. There are some new things we did there, but for the most part, this is, you consider this fairly generic hot trace formation, except that we do it a little bit more efficiently. Okay, but in terms of new stuff, the first optimization I want to talk about is dynamic value specialization. So what we're doing here is that we're going to now specialize the code for particular runtime values that we've observed. Now, there are compilers that do value specialization, so they make a guess based on, for instance, profiling that this method, for instance, always has an input of 1, and you can specialize for it. And if you're wrong, you can go execute the original code. But we're going to do it dynamically so that we can specialize on sort of runtime values that we couldn't guess before, or even values that change slowly. We can continue to specialize on this value, this value, this value, things that a static compiler can't do. And so this is going to have advantages over both software techniques and hardware techniques. The hardware technique in particular that's interesting is hardware value prediction. Hardware value prediction has been a concept that's been out there for a number of years, but has not been actually implemented in any real hardware. But what happens there is that you have this large structure that monitors the values of lots of instructions, and if a particular instruction continues to produce a 0 as its output, at some point you now start predicting as soon as you fetch the instruction that the output of that's going to be 0, and that allows you to execute dependent instructions before this instruction actually executes. We in particular apply it in our case to loads because that's where you can really get some gain with long latency instructions, decoupling the load from the dependent instructions. But if you do it all in hardware, right? So there are a number of problems. One is that you have to have this large structure because you have to be able to monitor a lot of values in order to be able to do these predictions. And there's a limit to sort of how many predictions you can do at once because it's actually expensive. You're injecting new values into the register file, et cetera. With our technique, we can make these predictions in the background, then we change the code, and then we don't need to monitor anymore. And we could execute 3 loads in one cycle if we wanted to, all of which they've been transformed because there's no hardware behind it at this point. There's just software. Allows us more sophisticated prediction techniques because we can think about these predictions in software if we want. But the things that really bias performance over hardware prediction is first that we propagate predicted values along the trace. Right? And so with hardware prediction, you have a load, you are really sure that this value is going to be 0, and you predict it for that load. But you then go and execute the very next instruction, you've forgotten that the value was a 0. But if you now apply it to the software like we do, you change the software, you can now propagate that 0 throughout the code. And you start doing things like dead code removal, branch elimination, strength reduction, things like that. And this propagation of these known values is really effective. And then those values being propagated can trigger other optimizations. Okay. Advantage over software value specialization, as I actually kind of mentioned before, is that we can adapt to semi-invariant runtime values. So something is 0 through half the program, and then 1 for a while, then 2 for a while. We can specialize to all those things, which is harder to do with static techniques.
So these values could be different across threads. So thread T1 could have one bunch of runtime values. Thread T2 could
Right.
So you would be doing a specialization for each thread of control?
So in fact, everything I'm going to assume, we're not really looking at multi-threaded programs, so we're talking about one thread program at a time. But I think the corollary, even in that context, is that a lot of times what you find is you could profile this and you could say this value is constant, but it's a lot harder to say it's constant and the value is 3, right? But yet when you actually start running it, you recognize the value is 3, you recognize the value is 2, you recognize the value is 1. Well, software techniques really can't take advantage of that, but a dynamic technique can because it sees it as 3, sees it as not changing, and then it adapts the code to it. And then you run a different time, and it's 2 and it's not changing, and you can adapt to that.
But in a given execution run, if there are 2 threads,
Yes.
and if a particular value is a constant, so in only one thread of execution and not in the other.
Well, so it depends. If this is a shared value, then either it's constant or it's not, because it's a shared value. If they each have private versions of this, right, and it is it's not a shared value, then you should be able to. You may or may not be, depending on the specific characters of the code, you may or may not be able to specialize, because if it's the exact same load that is executing this private version and this private version, then it's not going to appear as an invariant value to the hardware. And so, but if it's used by this one for a while and then used by this one for a while, then may have time to specialize here and then specialize here, just depending on how often they're interleaved. Yeah. Okay. All right. Okay. And the other thing is, because this is dynamic, sometimes you're just wrong, and we can detect that, but with a static change, you're just stuck with it. Okay. All right. So the sequence of things that happen, we're doing this in hardware. We create this hot trace, so things we've already talked about, that goes in the code cache. And once things are in the code cache, right, it's only then that we actually start monitoring some of these loads. And because we wait till that point, we don't actually have to monitor very many loads at once. And typically, we're just monitoring, the last loads we've added to the code cache. And then if at that point now we identify that this load keeps taking the same value, then we spawn a new helper thread, right, that does value specialization on those hot traces, puts new hot traces in the code cache, and then we start running those. Okay. And then we can get hot trace events on other loads, and so maybe in the same trace, we'll optimize for one load, and then another one becomes invariant, and so these traces can get better and better. Although just because of the latency of these helper threads, a lot of times, by the time we get one load, invariant load that sort of triggers a helper thread, by the time we actually the thread gets in there, gets triggered, and gets running, often all the loads that are semi-invariant have sort of identified themselves as, and so a lot of times, we end up even on the first event doing several loads at once. Okay. All right. Okay. So with dynamic value specialization, we are specializing for things that are constant, but we're also specializing for things that have strided values. And so we also have the ability in the hardware to not only recognize that this load is always loading 0, but maybe to notice that it is n plus 10, n plus 20, n plus 30, n plus 40 has a very strided behavior. And we can detect both these things in the hardware. And we now will use dynamic verification, right? Because we're going to now put the assumption into the hot trace that this load has this value. And so we have to actually verify that this is true. But we can do this actually with real simple software mechanisms that don't require any hardware support. And so let's assume that we have a hot trace that looks like this. It's got a load. It's got some instructions that, well, in this case, one instruction that depends on that load. And so you've got a long latency instruction, which potentially is waiting for this long latency load. Assuming it misses. But now we recognize that this load always produces the value 0. And so what we're going to do is, we've got the sequence here, is we are now going to perform the sequence, the original load, but write it into a scratch register, which hopefully we won't even need. We're going to move the predicted value into the original register. And now the dependent instructions now will stay the same. They'll still read the dependent values, so they won't change unless we can optimize them. We are going to compare these two values, right, and then branch back to the original code if in fact they are not equal, right? And so what happens here is that, right, assuming that most of the time we're right, what's going to happen is this branch is going to be predicted not taken, and it's going to have no impact on performance. But in the case where we're wrong, then all of the recovery is just done by standard branch mispredict, and with no need to add any hardware for recovering from value mispredicts. But the other thing that's going to happen is that we're also going to propagate this 0, so we can do things like strength reduction, because if we know R1 is 0, then we know R2 is going to be 0 as well. And because with value locality, it's been shown that most of the benefit of value prediction is actually arises from predicting that things are 0 or 1. And those actually provide lots of opportunities for things like strength reduction and dead code removal. Okay. Oh yeah, and so the key improvements here are really two. One is sort of the propagation and the strength reduction, but the other real key improvement that you get with any kind of value prediction scheme is that we have decoupled all this all the dependent instructions from this long latency original instruction. Okay. All right. So in terms of potential, one of the assumptions in our work, and certainly there are other ways you could apply this technique, but one of the assumptions in our work is that we don't really care about the load until it ends up in a hot trace. And so if the load is not in a hot trace, it actually is not a candidate for value specialization. And so we actually find that that actually there's a fair number of loads, but certainly most of our loads are candidates for value specialization. And of those, 16% total loads are actually value specialized once we've had enough time to sort of get these helper threads running. And so this makes sense that certainly not all loads have the ability to have enough value locality to be specialized, but certainly enough loads to have a real significant impact on performance, especially if these are loads that are missing. Okay, so another real interesting thing we want to know about this system is what is the overhead, because and certainly our overhead is going to be lower because it's happening in another thread, but it's still going to have impact on a multi-threaded system. And we assume a multi-thread system really for this reason. On a multi-core system, I mean the cost of running this extra code in another core is going to be almost zero. I mean you'll have some interactions at maybe the L2 cache, but that's about it. But in a multi-thread system, like an SMT system, you're going to be running instructions, using IQ entries in the L1 cache, and it's going to interfere a little bit with the main thread. What we found is that if we sort of do everything except actually use the optimizations, right? And so we're incurring the full overhead of the Trident system, but we're not actually getting any benefit from it. We only see about 0.6, less than 1% degradation of the main thread. And the reason for this is that our optimization threads are actually very efficient, and it turns out they're only running about 2% of the time, right? So they get in and out quickly. They do their optimization fast, and we actually pick up, the invariant values, really quickly. And then, sort of later on in our simulation, we're doing almost nothing. And so you can see this even though we're using another thread, if we're sort of space sharing this thread with normal execution, we have to take, almost no. We could run, be running another thread on this core or on this thread context and interrupt it very little to get full performance out of this. Okay. And actually, I'm not going to show. Well, actually, I'm going to show this graph, and I'm only going to show it once. Although we get almost the same graph for all of our optimizations. We're trying to do more and more aggressive things and use this compilation thread as much as we can, and we always end up with the same graph. Oh, this is the performance graph. So I didn't show any of the graphs, but I have this number. We always end up with the same number. We can't seem to get anything that uses more than about 2% execution time for these compilation threads. So we're continuing to look for more and more aggressive things we can do because there's really no reason not to be pushing these things further. Okay, in terms of performance, this is what we get. It really varies by the different spec applications that we're running. And what we've got here is hardware value prediction. So this is real standard aggressive value predictor that's been proposed. Obviously, nobody's ever built. This is sort of standard dynamic optimization, but using with all the advantages of our system, but not doing the value specialization on top of that, and then our value specialization. So there are sort of two interesting comparisons here. One is this comparison that says that we're getting twice the performance of a hardware value specialization. And hardware value prediction actually has a big advantage here, in the sense that we're really focusing on things that are in the hot traces, and we see that there's actually a fair number of loads that are now unavailable for that reason. And so here, hardware prediction is working on all possible loads. But the real difference between here is the fact that we sort of take this prediction and propagate it throughout the trace. And so we get further performance improvements from knowing that this value is a 0 or a 1 or what have you by actually changing the code after the load. The other interesting thing is that we actually don't get a lot of performance from doing real standard dynamic optimization, but yet it's critical to our whole system in the sense that that's the basis for everything we do and sort of provides foundation. Okay. So the next optimization is prefetching, and so what we're going to do is actually put new software prefetching into the code as a result of observed behavior. And so, you're probably all real familiar with prefetchers. There's compiler-based prefetchers that analyze the code and try and put in prefetchers, but they have difficulty dealing with non-deterministic input at predicting whether this load is going to miss in the L1 cache or L2 cache or not miss at all, things like that. Hardware prefetching can be very effective, but cannot follow real complicated load behaviors. They just predict. They just follow fairly predictable access patterns. And so we're going to do something now that's going to give us the benefits of both of these in the sense that we can pick up real dynamic behavior, but we can do much more intelligent things with it than the hardware prefetcher can. Okay. And so, again, the goal is to get this real flexible dynamic software system. And the things we're going to be concerned about is how are we going to get real accurate prefetching? And this is a thing that's really hard to do, especially statically. And we want to target the loads which actually miss in the cache, which you can do this profile driven, but profiles change with different inputs as well. And also, how do we cover the miss latency? And this is again a hard thing for a static system to do correctly. And we also want our prefetches to have real low overheads in terms of how many instructions it takes to pre-compute the address, so we can do the prefetch, things like that. Okay, so let me illustrate what the big problem is that makes getting the prefetch distance right, and that is the interaction between different loads that might be similar, either in a hot trace, maybe even the same basic block. And so let's say that these each had sort of different, expected latencies in such a way that the prefetch distances, assuming we actually knew what these latencies were, might be here. But the problem is that the place you would want to actually do the prefetch for this instruction to have it really show up at just the right time, because you don't want to have it coming too late, because then you stall, and you don't want to have it coming too early, because you might replace something useful in the cache, or you might actually have it replaced before the load actually comes. And so you want it to show up at just the right time. But the problem is that where I put the prefetch for this one depends on what I assume about this one and this one. Not to mention whether my assumption about whether what level of the cache this guy misses in is correct. And so this is only right if actually all three of my assumptions are right. And that's okay. So maybe you actually get those right. And so you put all these prefetches in the right place. But now this prefetch actually starts working, right? So your assumptions about this guy's prefetch distance is wrong. So now these guys' prefetch is now happening at the wrong time, and you have to move them. And maybe but then the fact that now this guy is no longer being covered because his prefetch distance is wrong affects this guy, and they interact in such a ways that especially statically, it's almost impossible to get it right. And so. So we really need a dynamic technique that's going to allow us to just discover the right distances instead of pre-compute them. And almost any conventional system is, if they're lucky, they're going to get, come close to getting it right once and then just leave it and certainly not be able to adapt to changing behavior. Okay. So in terms of our dynamic prefetcher, we're looking at two events: the hot branch event, which again creates our hot traces, and now a delinquent load event, where this event just says, here's a load that frequently misses in the cache. And hopefully we also get some information about what the expected latency is going to be, but we'll find that even that isn't really necessary. Okay, and so then once we have that event, we'll create a thread that's going to go through the hot trace and insert some prefetching. Okay, and so there's been some other, there was some other work that actually does, some thread-based dynamic prefetch distance estimation. But again, what they do is they use dynamic information to make a pretty good estimate of where the prefetch could be. But they still just make this one estimate they hope it's right, and then they go on, and then when they start sort of correctly prefetching other loads, then then it's going to be wrong and not be able to adapt. And again, so ours actually could take advantage of this. Turns out we actually don't, because determining these two things is actually somewhat expensive in hardware. Detecting load miss latency and measuring cycles per iteration. But we could, and we could assume that we actually model that and then find that it doesn't actually help us at all. Okay, so we also do several other optimizations that Weifeng did that they're somewhat orthogonal. One of those is doing whole object prefetching. This is useful, one, because it minimizes prefetch overhead, but the other reason it's real helpful is that it makes our repairing of prefetch distances really fast, because we've sort of aggregated all these prefetches, and then we just need to change a couple of numbers and all in the same manner to sort of prefetch the whole object an iteration earlier than we thought we needed to. And that's probably all I want to say about that. But the main optimization is adaptive prefetching, and again, it's just the interaction between the different loads that creates the biggest problem. You also have some controlled flow issues, but the main problem is just the interactions. And so what we do, and again, instead of actually starting with this sort of complex, but at least initially fairly accurate estimation of how many iterations ahead we should prefetch, we just start out with an initial prefetch distance of one iteration. And so what happens there is we start out prefetching one iteration ahead, and if it turns out we're wrong, that's not far enough, well, we get another delinquent load event. So we change it to 2. We get another delinquent load event, we change it to 3, and then we no longer get delinquent load events, and we're fine, right? Well, now some other load starts doing something funny, and well, now 3 is not enough anymore, and so we change it to 4. And eventually it comes out right. And so it turns out, rather than just be smart about it, this trial and error method is just really effective at adapting. And the whole key to this is the fact that our optimization system is so efficient and has such low overhead, again with hardware monitoring and the optimization done on another thread, that we can do trial and error type of optimizations on things that just cannot be estimated or computed deterministically. And we tend to stabilize, although we talk about trial and error, we tend to stabilize real quickly. In fact, I didn't even really want to go through the example of sort of going back and forth, but we do have the ability to sort of back up if our sort of computed average load latency goes up as we continue to increase, we can sort of back down again and find the right spot. Okay, so a real interesting advantage of our system over other prefetching systems is that we found, so certainly we have a problem like most systems do with pointer tracing loads. It's just really hard to prefetch these. The issue is that with pointer tracing loads, we have these loads that are not only hard to predict, but they also are dependent on each other. And so you can create this software prefetcher, or even we'll talk about helper thread prefetching, that sort of follows this chain and tries to get ahead of the main thread. But often the main thread runs as fast as it can follow this pointer chain, and so having the prefetches that execute as fast as they can follow this pointer chain isn't any faster than the main thread could go anyway. And so it's very hard to and it's hard to prefetch. You can prefetch one iteration ahead. Once you get the pointer, you can sort of prefetch the target immediately, but it's really hard to prefetch. It's very expensive to prefetch multiple iterations ahead, and you can only do that, and you incur a cache miss to do that because of the dependencies of these threads. So it's very difficult. One of the things that we found is that for a lot of applications and a lot of pointer tracing loads, they actually have strided patterns, and so we've got this hardware that can detect loads that have constant values but also strided values. We think we're looking for things that sort of stride through arrays. Well, it turns out a lot of the things that jump out are things that are pointer tracing loads, and things that you look at the code and you try and figure out the recurrence, and it's this really complex thing when really the addresses it's seeing are n plus 100, n plus 200, and a lot of reason for that. If you look at the way these codes are structured, they'll do things like allocate this linked list in very sequential fashion. And so all of these mallocs come one right after another, or they're even done by hand. You malloc this large space and you divide it up, in the code. and then create links between these. And so you find that there's a lot of code that has this very, very, especially if you look at the virtual addresses, that have this very, very linear movement through memory. And so now you can take these and use real simple strided prefetches to prefetch pointer loads. It gives us a real advantage over really any existing prefetch system. Okay, and so in terms of caches now, in terms of cache miss coverage, now we can sort of prefetch over half the loads. Again, we can only do loads that are in hot traces. This is a different study, so we're actually getting more loads in the hot traces than we were before, and we can get over half of those prefetched for various reasons. Okay, okay, and then the performance is so the performance is over 20% gain from the self-repairing prefetching. Comparing this, for instance, with a more conventional, this is actually a pretty aggressive prefetcher, which actually has most of the advantages of our system. So we're not modeling just sort of standard software prefetching. We're modeling a dynamic system that takes advantage of a lot of dynamic behavior, but does not have the ability to adapt and repair the way that ours does. And we get, basically double the performance of a technique that doesn't do the repairing. So you see the advantage of really being able to adapt as the interactions change between the loads. Okay. All right. So another thing we wanted to do, right, and there's a little bit of overlap with this, but we'll actually find that that they actually work together quite well, is helper thread-based prefetching. So things like speculative precomputation that we've worked on, but a lot of other people have as well. Right. So another way that you can do prefetching is, obviously the one way is doing software prefetching with the prefetches inline with the code, and the other is that you can put the prefetches in a separate thread, something that by itself has been done before, but obviously the difference here is that we're going to create these threads dynamically as we're running. So we start out with code with sort of no support for thread-based prefetching, and we're going to actually create these helper thread prefetchers as we go. And so again, a lot of prior research that sort of defined this thread-based prefetching and shown it to be real effective, and certainly the ability to handle loads that software prefetching cannot prefetch as effectively. And so again, the idea here is that with helper thread-based prefetching is that you have this helper thread that has the ability and has the ability by pre-computing a subset of the instructions between the trigger and the delinquent load. And so you will trigger this thread, you will execute a prefetch, and hopefully now you'll be able to cover the memory latency by getting here faster than you get here, because this is only executing a subset of these instructions. And if you do, then you cover the cache miss latency. And now the helper thread runs, and the prefetcher runs decoupled now from the main thread. Okay. And we typically do that by just stealing code from the main thread. So you can now capture recurrences that a hardware prefetcher or even a lot of static prefetchers can't deal with. And it works best when we actually are able to create a looping thread so that we trigger one thread and it does a lot of prefetches. Okay. So typically what this work does, I'm going to go through this quickly instead of stepping through it slowly, is finds the delinquent loads. It sort of finds the instructions that this is dependent on, and so it creates a slice that pre-computes the addresses of these things. Puts all the instructions from that slice in a separate thread, changes the loads to prefetches, and then we execute this. The P thread, the prefetching thread, before we, hopefully faster than the code can get here. Obviously, this is a small example, so not much opportunity to get ahead. But particularly if we can now do this in a loop, now this becomes a loop that hopefully runs much quicker than this loop does, and that this thing can get farther and further ahead. Okay. So again, there's a potential for this pre-computation-based prefetching to be more effective than inline prefetching. Can certainly handle more loads and some more complex loads. But there's also more things to get, that you need to get right for this to work well. Not only do you have the dependence on, what the latency of this load is and maybe interactions with other loads, But you also have new things which are, we have to make more decisions about sort of where to trigger this thing and sort of when to kill it because it's gotten too far, because we're not executing those loads anymore. Things like there's even this dependence on the control flow that we didn't really have as much before. So if our assumptions about the control flow change, then our helper thread needs to change, things like that. But our ability to now adapt, because our optimizations are quick and we can sort of detect when things are going badly, is real key here. So, so we do our initial design, and as in sort of all of these pre-computation-based optimizations. One of the big problems is just getting far enough ahead of the main thread so that our prefetches are timely. And so we have a whole sort of slew of optimizations we do to sort of get the P thread out in front. But the main point here is that we have the ability to first of all, analyze the code, to then optimize the code based on those behaviors, knowing which loads are delinquent and which ones aren't, to do these prefetches, and actually now create these threads that pre-compute the loads ahead of time. And I'll just gloss over some of the optimizations. And so we get now performance that is still better than sort of pre-existing techniques that do helper thread prefetching, even assuming ones that sort of have a lot of the dynamic information that we have. And again, a big part of these gains are the fact that things like where you should trigger it, how many iterations ahead you should start prefetching, what your sort of target prefetch distance should be, because we'll have some mechanisms that prevent the P thread from getting too far ahead of the main thread. Things like that, again, are hard to determine statically, but we can just sort of do some trial and error again to kind of find the right values for each of those. So the adaptation is key. We do have this mechanism because, again, we've got this mechanism similar to the previous topic, where we have these pointer chasing loads that now we actually find they have strided values. And so now a lot of our strides are actually predictions as opposed to sort of guaranteed values. But even if your control flow's predictable but not perfectly predictable, you'll find even with strided loads that occasionally you'll be wrong. And you might sort of get out of sync and things. And it turns out there are a couple applications where these strides would be extremely accurate for long periods of time, and then there would just be this big gap that we wouldn't see, and then it would be off, and it would stay off. And so just having a mechanism that actually detected when what the prefetcher was doing was really different than what the main thread was doing was really valuable, and we could just kill that. Actually, we had a mechanism, Weifeng had that could actually really quickly find the base address, a new base address, and replace the old base address to get back on track without actually killing the helper thread. And it turns out, particularly in a couple applications, this was really important, which improved our average performance. And you might also think that this was pretty redundant with our software prefetching, but actually we find that they actually work well together, because particularly the thread-based prefetching can prefetch loads that are really hard to prefetch with software prefetching. And so even when we combine these together, we get 10% better performance with our helper thread prefetching on top of our inline prefetching. Okay, so bottom line, event-driven multi-threaded optimization or event-driven compilation. It's event-driven because we're looking for interesting things in the hardware that indicate runtime behavior that we can take advantage of. And we take those events, we fork threads to change the code, to adapt to those, and the threads go away. Because the compilation takes place in parallel, because the monitoring is really low overhead, it allows us to do really aggressive optimizations. Again, much more aggressive than we're actually doing now, because we have all kinds of room for more runtime for these threads. We can do these gradual improvement with recurrent optimizations, which means the threads can get better and better. We can even do these trial and error search-based optimizations where things just aren't as predictable as we'd like. Okay. Any questions? Yeah.
you have a slide that combines all the techniques you talked about today?
Not yet. We're still working on that. No, actually, it's something that we want to see. We just don't have that particular result yet.
Then do you have any feeling for? I guess there may not be a theoretical ceiling to those warnings, but do you have a feeling of what some sort of ceiling would be? Performance gain capability.
For all three of these together.
Yeah, I mean, like when you introduce significant code changes like this, it's hard to say some theoretical bound.
Yeah. I mean, the one unfortunate thing is these are really all targeting the same phenomenon, which is the latency of loads. Although the value specialization gets some additional optimizations through the propagation of known values, but still a big part of the effect is just decoupling the loads from the dependent instructions.
So you could just run with the perfect cache.
The perfect cache would be a pretty good guess at what the optimal result from all three. And the reality is that hopefully we'd get pretty close to that because we're attacking loads in three different ways here and hopefully capturing hopefully a pretty high percentage of them. But obviously we're not restricted to attacking loads, but everything we've done so far attacks loads. So that would be a limit. But in the future, hopefully we'll find new ways to apply this for other problems.
How much hardware support do you need for these optimizations?
So the hardware support is not insignificant, right? So it's not at the level of sort of current processor monitoring where you're counting instructions or you're counting branches or branch misses and things like that. So doing, for instance, value. The delinquent load table I think is not certainly a crazy amount of hardware and I think actually current processors aren't that far from identifying sort of particular loads that are problematic. The value specialization is a little bit tougher because you're sort of pulling values at the commit stage and storing them and monitoring them and even detecting strides, which require a subtract. But the one thing we found is that we don't need a real big table for the value locality profiling like you would for a hardware value prediction, right? Because we're really monitoring a fairly small number of loads at a time. We create a hot trace and we sort of put those loads in the table. And by the time we get around to, sort of create another hot trace, right? Because it takes, many thousands of instructions to actually, create hot trace. So by the time we have, put another hot trace in the code cache, we've probably already determined at that point whether these values have locality or not. And so the number of values that you have to monitor at once to get decent performance, I think, is fairly low in the range of 8. So one element of this table is not insignificant, but the table itself is actually real small for that reason, right? Whereas a technique that sort of has to continuously monitor a lot of values to be useful, like hardware value prediction, is going to be much, much bigger. So I would not say it's on the level of most of the things, the real simple things are being monitored now, but it's not. I certainly wouldn't call it extravagant and probably reasonable for the next generation of processors.
Any more questions?
All right.
Thanks, Dean.